What's up, AP Precalc students? Let's do homework 2.3. Homework 2.3 focuses on the concept of the fundamental theorem of algebra, which says whatever your degree of your polynomial is, that's how many roots you have. Your degree equals your roots. Your roots meaning your x-intercepts, your zeros, all of that stuff. Okay, so we see 1, 2, 3. If I distributed this out, we would have an x cubed. You're going to have 3 roots. Now, what happens though is sometimes you'll have real roots and sometimes you'll have imaginary roots. We discovered in class how imaginary roots always work in pairs, or else you won't have a polynomial if you distribute a factored form with just one imaginary root. So we're keeping that all in mind. A root could have a multiplicity. That is counting as an amount of roots. If your multiplicity is 2, you'd count that twice. That's one solution that occurs twice. That's like 2 of your roots. Okay. So I get x equals 1. I'm setting these equal to 0. I'm going to try to factor. Hopefully I can. X plus 4, x minus 1, that does. So x equals negative 4, x equals 1 again. X equals 1 has a multiplicity of 2. It's going to be a bounce, a no sign change. There's our 3. 1 occurs twice, and x equals negative 4. Remember, when x, a form of x, is all the way factored out, x equals 0 could be a 0. Here we got x equals negative 2. I'm hoping I could factor. I can. X plus 7, x plus 2. Oh, hey, look at that. X plus 2 occurs twice. That means this has a multiplicity of 2. And x equals negative 7. 1, 2, 3, 4. 1, 2, 3, 4, x to the 4th. This is an x to the 4th. I'm going to have 4. There's my 4. 1, 2, 3. I'm going to have 3 roots, x cubed. What are my roots? Well, I got my first root, x equals 0 from x. My second root, we can't factor x squared plus 16. Remember, x squared plus 16 is not x plus 4 times x plus 4. X plus 4 times x plus 4 is x squared plus 8x plus 16. X squared plus 16 can factor, but it's using imaginary roots. We subtract 16, we take the square root. Remember, the square root of negative 16 is the square root of 16 and the square root of I. We get this, the square root of 16 and the square root of negative 1. We get this plus or minus 4i, meaning this can factor to be x plus 4i and x minus 4i. That shows the pair of complex solutions that we have. Here is our one real solution, and all of our previous ones we had real solutions. We had our plus or minus 4i as our complex solutions. We still have 3. Complex solutions have to occur in pairs, or if they didn't, then you're not going to have a polynomial. If you just have x times x plus 4i, you'd get x squared plus 4ix. That is not something you can plug into a graphing calculator, and you have this polynomial. So you have to have pairs, because if you distributed this, and we showed this in one example, if you distributed this, the 4i's times the 4i's would give you negative 16i squared. I squared is just negative 1, so that would give you that positive 16. Anyways, I digress. This is a 1, 2, 3, 4. This is an x to the 4th. We're going to have 4. We see x equals 0 as a real. We can see x equals 3 as a real. We can't factor this. To solve x squared plus 9 equals 0, we would subtract 9. We would square root. We get plus or minus 3i. Those are our pair of complex solutions, 1, 2, 3, 4. 2 real, 2 complex. combining to be 4. Just because 2 is factored out does not mean x equals 0 is going to be a factor. You need an x out there. We have 1, 2, 3 x's. This is x cubed. We get a real one at x equals 3. X squared plus 1, subtract 1, x equals plus or minus I. The square root of negative 1 is I. 1 real, 2 imaginaries gives us our 3 roots that we're looking for. We might have to factor. We hope to factor some more. 2 numbers that multiply to get 5 and add to get 4. Can't be done. Now, the question asks us for the number. We know we have 4. I can see we have 2 reals right here. X equals 0, multiplicity of 2 are 2 of our roots. I try to factor, and I can't. I think the 5 and the 4 need to be switched because of the positives. I'd have to use the quadratic formula to get these answers, or you could complete the square. I'd have to subtract 1. We'd have a square root of negative 1. The question asks you how many. You know you're going to have 2 complex. You don't have to know this, but like if you use the quadratic formula, you could see you're going to get the square root of negative 1. Let's just do it. X equals the opposite of b over 2a, plus or minus square root of b squared, 16, minus 4 times 1 times 5. 4 times 1 times 5 is 20. Square root of 16 minus 20 is the square root of negative 4, all over 2a. We get x equals negative 2 plus or minus. This is 2I over 2. That's just plus or minus I. If we completed the square, we would see the same thing. Boom, those are our 2 complex that I could kind of just tell by knowing we couldn't factor and by kind of checking with the idea of the quadratic formula, whatever's in the square root, b squared minus 4ac. That's called the discriminant. So negative 2 plus or minus I are our 2 complex. D is my favorite. It's Huff's favorite too. Let's see. I'm going to factor out a 3x squared, giving me x equals 0 as a multiplicity of 2. I can see it's an x to the 4th. X to the 4th, I'm going to have 4. I get x squared minus 4x plus 20. I got 5 and 4. I got 10 and 2. I got nothing is what I got. Okay. This can't factor. We could use the quadratic formula. Think about the b squared minus 4ac. So opposite of b over 2a, plus or minus square root b squared, 16 minus 4 times 1 times 20. 16 minus 80 is negative 64, all over 2a. We get this 2 plus or minus 8i over 2. That's 4i. X equals 2 plus or minus 4i are our 2 complex. We didn't have to find them in the question. We just had to see how many do we have. There you go. It's like, this is important because on your test, you don't necessarily have to find them. You do have to know how many there are and like use that information to your advantage. X to the 4th, there's going to be 4. Now, I actually can factor this to be x squared minus 4x squared plus 4. Why could I do this? This is a difference of squares. This is x squared squared. This is 4 squared. It's a difference of squares. X squared minus 4 times x squared plus 4 is x squared x to the 4th minus 16. Now, x squared minus 4 can be factored to be x plus 2, x minus 2, giving us 2 solutions, x equals positive or negative 2. The other 2 have to come from here. You're going to have complex ones. You'll have x equals plus or minus 2i, the square root of negative 4. There's my 4, 2 real, 2 complex. You did not have to find the complex, but this just kind of shows you. Because these questions are questions that like you don't have to like do a lot of algebraic work, but you have to understand this idea that complex roots have to come in pairs, because if they didn't, you wouldn't have a polynomial. If you have x minus 4, you see x equals 4 has to be a root. You have x minus I. This is a listed factor, but it's not all of my factors. It's not saying these are all of my factors. If x minus I is a factor, guess what? X plus I has to be a factor. The conjugate, the pair that goes with x minus I has to be included. The question is determine the least possible value of n. This has got to be at least a cubic, because I have one real and I can't just have one imaginary. I have to have even amounts of imaginaries, even amounts of complex. Here, I have one complex. Well, I have to have two complex at least. I have three reals coming from here, 3, 4, 5. This has to be some sort of x to the fifth. This is just testing you on your have to have a pair of complex roots, okay? X equals 3, multiplicity of 2. X equals negative 4, multiplicity of 1. One complex, well, if you have one, you have to have two. This is how I know I'm going to have an x to the fifth. X equals 0, multiplicity of 2. X equals negative 2, multiplicity of 1. There's one complex root. I'm going to have a second, at least. This has to be an x to the fifth. It's a little bit like redundant. Oh, this is a good one. X minus 2i. X plus 2i is its pair, is its partner. It's the plus or minus an amount of I. That's it. You don't have to have 4. The least possible value are these two complex roots, and then the 4 real roots we see at x equals 2. This does not have to be more than 6. This is just 6. You're given the complex roots. Okay, the rest are pretty easy. Like you're giving graphs, and you're either understanding what the power could be, or something else. Like just see what we have. Like we have 4 complex roots, we're told. What is the minimum possible degree of p? This is the graph of p. Well, we can see p's got 2 real solutions right there. Like, so we can see that we're passing through at those real solutions. We're not bending. So we're thinking of this as like being y equals x multiplicities, like a multiplicity of 1. So here's one root, multiplicity is 1. Here's another root, multiplicity is 1.
Another package for you.
Thanks. Thanks, Patak. We got 4 complex roots. We have to have a 6th power. That's our minimum. Okay. Here's a root. There's a root. Multiplicity 1, multiplicity 1. We're going to have to be an x to the 6th. We can see it has to be an even degree, right? Because of our end behavior. But it's not going to be an x squared because I have 4 complex roots. We can see this has to be an odd degree because of the end behavior. We are y equals x cubing it, positive x cubing it. We can see we have a bounce at 3. So that means, x equals 3's got a multiplicity of 2. That means x minus 3 squared is a factor. We can see a bend at 1. So that means x equals 1 being a multiplicity of 3. X minus 1 cubed has to be a factor. That's 5. We have 4 complex root as well. 6, 7, 8, 9. This has to be an x to the 9th. We knew it had to be odd. We see a double root, a triple root. We're going to have 5 reals plus 4 more. We got a 5th degree polynomial. We could see one real root. Its multiplicity is 1 because it's a pass through. It's like y equals x. If it's a 5th degree polynomial with one real root, you're going to have 4 complex zeros. They have to come in pairs. That's it. Fundamental theorem of algebra, very simple. Degree equals roots. This is a 6-degree polynomial. I see a double root here. We got a multiplicity of 2. It's occurring twice. We got a single root here. Multiplicity is 1. So I'm already at the third power. That's also a multiplicity of 1. So I'm a fourth power. I'm going to have 2 complex. I got 4. We're a 6th degree. We got to be x to the 6th. So 4 real, 2 have to be complex to get to an x to the 6th. Cool. Then we got to these differences. This is like, now for something different. We learned last unit that quadratics rates of change had the rate of change of the rate of change was constant. We're going to call those differences now. And we would say quadratics had constant second differences. It can be shown that cubics have constant third differences. The change of the change of the change will be constant. Quartic, x to the 4th powers, have constant fourth differences. The change of the change of the change of the change. Now, why? You won't learn why until you get to calculus. Which is why I don't know why we're doing this. But like, it's still fun kind of stuff. We're going to look at differences of differences until they're constant. And that'll be our understanding. We know linear functions, x to the first, had constant differences. The rates of change were consistent. It was the slope. So anyways, let's have some fun. Differences. Negative 16 to 0, 0 to 4, 4 to 2, 2 to 0, 0 to 4, 4 to 20. Okay, it's not a linear. Positive 16 to positive 4. Positive 4 to negative 2. Negative 2 to negative 2. Negative 2 to positive 4. Positive 4 to positive 16. Negative 12 to negative 6. Negative 6 to 0. 0 to 6. 6 to 12. First differences. Second differences. Third differences. This is a cubic. Cool. Horizontal tables. 44 to 0. Minus 44. 0 to 2. Minus 2. Negative 2. 0 to negative 2. Negative 2 to 2. Plus 4. 2 to 0. Minus 2. 0 to 4. Plus 4. 4 to 50. This is going to be a fun one, guys. 46. Like, I made these, so I know they work out. I used Excel. It was great. Minus 44 to minus 2 is plus 42. Negative 2 to 4 plus 6. I hope this works out. Negative 4 to 2. Negative 4, positive 4 to negative 2 is minus 6. Negative 2 to positive 4, again plus 6. 4 to 46 plus 42. Okay. These are so funny. 42 to 6. 36 minus 36. 6 to negative 6 minus 12. Negative 6 to positive 6 plus 12. 6 to 42 plus 36. Negative 36 to negative 12. Positive 24. Negative 12 to positive 12 plus 24. Who came up with this one? Did I come up with this one? 12 to 36 plus 24. First differences, second differences, third differences. The fourth differences are constant. This must be an x to the fourth, a quartic. I think these are so silly. You don't understand why this is going to be the case until you get to the calculus. It's just like going on faith, which I don't like doing. Oh, this is great. P is a cubic polynomial. Fill in the missing table value. I laugh at this because it's like we're going to have to find the third differences and back our way out of this. So let's go. Minus 15 minus 3 plus 3 plus 3 minus 3 plus 12 plus 6 plus 0 minus 6. Okay, here we go. Minus 6 minus 6 minus 6. Okay. That means our next one has to be minus 6. Okay. So that means this has to be a minus 12. Okay. And if that's minus 12, this has to be a minus 15. Let's talk about this and make sure we get this, okay? Once we know the third difference is negative 6 across the board, then this has to be a minus 6, okay? So we can see like 12 minus 6 is 6. 6 minus 6 is 0. 0 minus 6 is 6. 15 plus 12 is negative 3. Negative 3 plus 6 is positive 3. Positive 3 plus 0 is positive 3. Positive 3 minus 6 is negative 3. Okay. Negative 6 minus 6 is negative 12. Negative 3 minus 12 is minus 15. 2 minus 15 is negative 13. What a fun little question here. Constant differences, a little silly. You're required to know it for some reason. Fun little problems. I can't wait to do them in class today, actually. I forgot about these, that we were doing them. Anyways, should be fun. Friday. This is good stuff. Later, guys.